This is Junior Kangaroo from 2023, just a few days ago. Let's just do it. With a question like this, you could be intelligent, or you could just try stuff by putting in three threes, which obviously doesn't work. And then when you put in four fours, it does. And so you have your answer. Good. Question number two, ages of the sum are this. I mean, in 3 years' time, they're all 3 years older. So you have to add 3 years for this person, 3 years for this person, and 3 years for this person. So add three lots of three onto that total to get 40. And that's the first couple of questions. This kind of thing is just trying stuff. You've got a nice picture to work with, so just try stuff. You're only allowed to turn right. So here we have to turn right, otherwise we'll go head first into the wall. So turn right, I guess. I'm going to go as far as I can before turning right again, because it feels like getting into this mess is not helpful, right? You're just going to make a square. So go down here as far as you can, and then go as far as you can again, and then go as far as you can again, and you get to Q, and it will only take a few turns, which is good. The answer is B. Question four was the only question that I actually got wrong here because I didn't read the question. That's a good tip for all of you. He's taking four pills, except this is the time where he took his first pill, so he only has three to take. So it's 3 times 75 is 225, which is 3 hours and 45 minutes. So he's going to take his last one 3 hours and 45 minutes after this. 3 hours after that is 14, and then plus 45 to that makes 1450. This question I had to skip because I genuinely didn't understand how the answer wasn't just three regions until I eventually realized I did the entire paper, came back to it before realizing that you could tilt one of the squares, and then I just felt like a complete moron for about an hour. Anyway, the answer is E. Question six, you just have to test all the things between 20 and 30. You can't divide by 0, so that's not. This is divisible by 1, so great. This is divisible by 2. This is not divisible by 3. This is divisible by 4. This is divisible by 5. Not divisible by 6. Not divisible by 7. Not divisible by 8. Not divisible by 9. Not divisible by 0. The answer is 4 of them. Next one, just try putting this shape in here. You could think about this much more logically, but basically, I tried for like 2 minutes just drawing random things on squares, and I could never fit more than four in. It feels very illogical that you could actually find a way to get another block in here, because you've only got four squares left, and they'd have to line up perfectly into this T shape. And just because of the fact this is 5 across and this is 4 down, nothing works to line these up perfectly. So pretty confident the answer is 4. You could prove it, but this is a math challenge, so you don't want to waste time doing that. If you're 95% sure of the answer, just underline it and move on. Peter the Penguin likes catching fish. He realized he caught 3 times as many as he actually did. He would have had 24 more fish. So if we caught X, the number of fish he caught, if we times that by 3, that's 24 plus the amount he caught. So 3x is x plus 24. Take away x from both sides, divide by 2, and we get x is 12. 9 then, I always talk about this particular one here with my classes whenever we do perimeter. The perimeter of this L shape here is the same as the perimeter of the box around it, because you could just imagine sliding that length to the top and sliding that length to the side, and you just end up with that same shape all around the way around. So this is a shape that has the same perimeter as the square that contains it. Now this one doesn't, because if you slide this here and this here, you've got all of these extra perimeters that are left over, so that doesn't work. Nor does this, because you slide this here, but these are left over. But these all work because you slide, you slide, you slide, you slide. That makes a perfect square. Slide across, slide down, slide across, slide down works. And then these ones, of course, slide onto the corners. And so you have 4 of them that work. Here, so we're looking at from this direction. We can see on the left-hand side there are 4 blocks is the highest amount. It's almost like a staircase on this left-hand side here. So if you're looking at this from the front position, the left row will be 4 high. Because, you know, if you imagine standing at the bottom of a staircase, you can see the top stair, right? It looks as tall as the actual staircase is. So we're going to see 4 on this side. We're going to see 3 on this row, because again, that's the highest number. We're going to see 3 here and then 2 here. So it goes 4, 3, 3, 2, and the answer will be E in terms of what we can see. 5 candidates got a number of votes. There was 36 votes in total. Winner got 12. Last place got 4. So 36 minus 12 minus 4 is 20 votes to go between the remaining 3 candidates. None of them got the same number. So we just need to find combinations to make 20 where no number is the same, and we have to be more than 4 and less than 12, because otherwise they wouldn't be winning and losing. So 5 plus 7 plus 8 works, so that's one option. So does 5 plus 6 plus 9. The only other option you can go with is 5, 6, and 7, 7, but that's the same number, so that doesn't work. And so the second place candidate could get either 8 or 9 votes just by trying stuff. Again, trying stuff just a really important method in Math Challenge. A regular cube has 6 faces, 3 at the back, 3 that we can see at the front. If you cut out this cube like this here, you don't lose any faces because these faces are just L shapes instead. But you do gain these 3 here. So this shape has 6 plus 3 to make 9 faces. Now, if you do that same process with all 8 corners or vertices, that will increase your original 6-faced shape by 8 lots of 3. So we're just going to do 6 plus 8 lots of 3, which I think makes 30. And this is just all the stuff that I said out loud written down for some reason. How many pairs of 2-digit positive integers have a difference of 50? So 60 minus 10 would be the obvious one to start with, but then you could just roll on up 61, 11, 62, 12, all the way up to, I believe, 99, 49. And of course, the difference between 10 and 49 is 40, because it's almost like the difference between 11 and 50. So counting from 1 to 50, I guess you could think of it as. Anyway, the difference is 40. Lots of goals scored in the match. In the first half, 6 goals were scored, and the away team was leading. So the possible scores are 6-0. This is the away team here winning. 5-1 or 4-2. Can't be 3-3 because that's a draw at half-time. In the second half, the home team scored 3 goals and won the game. So this is the home team, remember. The only time in which they could score 3 goals and win the game is clearly this one here to make the score 4-5 to the home team. And so they scored 5 goals in total overall. Question 15, 3 Sundays are prime of the dates. Just try stuff again, once again. Just put Sunday on the first day, which means these will all be on these will be the Sundays for that month. And then you just look for prime. So not prime, not prime, not prime, not prime. Prime, so that's not very successful. Move Sunday to the second day of the month, and we get prime, not prime, not prime, prime, not prime, which is only 2 of them, I believe. Move Sunday to the third month, prime, prime, prime. That's 3 of them. Perfect. It's a 31-month day, but I'm assuming that's allowed. Sunday was the 3rd of the month, so therefore Monday is the 4th, Tuesday is the 5th, Wednesday is the 6th, and Thursday will be the 7th, and the answer will be A. With this one here, is this the 10th time I've said this in 16 questions? Just try stuff. Start with 3 here, and what happens if you do 4 and 2? Which seems like it could be a fairly obvious thing to try. Every square has to be 1 away from the one next to it, so this has to be a 3 because that's the only number that's 1 away from 4 and 1 away from 2. So that has to be a 3, and then maybe this has to be a 3 as well. It doesn't have to be a 3, and we're going down here anyway. We're trying to get a 9 somewhere. So if you're trying to get a 9 somewhere, you have to try getting upwards. So let's go from 4 to 5. This has to be a 4 though. And then let's try and go again as high as we can. This just doesn't end up working at all. You don't get anywhere near as high. So okay, what we have to do is say, what if we just go high to start? 4 and 4, that makes, you can use the 5 here because that's 1 away from both 4 and 4. You can put a 5 here, you can put a 6 here, and you end up building this up and getting to 9 eventually. There's actually a much, much easier way to do that than just trying stuff, which is to logically deduce that if the grid starts with a 3 and there is a 9 somewhere, and you can only go up in gaps of 1, that means you just must have every number from 3 to 9. So 3, 4, 5, 6, 7, 8, 9 appear somewhere. And what you know, that's, I believe, 7 numbers in total, without actually having to fill in the grid at all. So yeah, kind of interesting. These questions are always fun. These people are all called Boris, and they lie at all times. I'm sorry, does that demonetize my channel? Who cares? Ali says my stone is the same color as Bev's, but he's lying, so their stones are different colors. So therefore, one of them has a red one and one of them has a green one. Bev says my stone is the same color as Chaz, so they also have different colors, which is interesting because that means that if Ali and Bev have different colors and Bev and Chaz have different colors, like imagine Ali is red, Bev is green. Bev is green, that means Chaz is red, and either way you do that round, Ali and Chaz have the same color, which I think means we can just immediately go to the answer. Oh no, we can't, because Chaz says exactly 2 have red stones, but he's lying, so therefore there are 2 green stones. So the people who have the same color, which is Ali and Chaz, both have green stones, and Ali's stone is green is one of the true statements, and none of the others are. Good. 18. There are 66 cats. Don't like 21 of them. So 66 minus 21 means you like 45. Of those 45, 32 have stripes, 27 have a black ear. But the number who have both of those things as small as possible, well, if you add these two numbers up, you get to like 59, which is too many cats. So at the very least, 14 of them must be being double counted when you add these two numbers up. So 14 at the very least have both things. A group of 40 boys and 28 girls stand in a circle facing inwards. 18 of the boys give their right hand to a girl. That means 22 of the boys give their right hand to a boy, which means that 22 of the boys give their left hand to a boy because you were just considering the 22 boys to the right, right? Like if you've got boy A giving his right hand to boy B on his right, that means boy B is giving his left hand to boy A, and you've got the same number of boys doing that, so that's fine. But now, of course, 22 boys give their left hand to a boy means 18, the other 18 boys give their give their left hand to a girl, which is the answer to the question, and we'll just end up with 18 here. 20 then, I don't know how, there's some algebra, there's an algebraic way of doing this, which maybe I was thinking of trying here. I don't know what this is about. Oh, I remember how I did this. I changed the question to, instead of thinking about minusing numbers, a minus b equals c, where a and c have reverse digits and b is this number here, I thought about just adding numbers together because I thought that would make the question easier. So instead of considering a minus 297 equals c, just consider c plus 297 equals a, just because I thought adding numbers was easier than subtracting them. And then I just tried stuff until I found a way to make this work. I found that eventually. I can't stress enough, I just found that by chance. I just found this by chance and then thought, okay, well, now that I have one working solution, what small change could I possibly make and still end up with a working solution? Well, if you increase the 4 to a 5, that doesn't work. You just end up going completely wrong. But if you increase the 0 to a 1, if you increase the tens column, it magically still works. So therefore, if I keep increasing the tens column, and I tried a couple of these, but I was pretty confident that was just a system that would work. So I then said that anything that starts 1 something 4 is just a thing that works. And there's 10 of those, right? From 0 to 9, 10 digits that work in the middle. So 10 of those. And then the next logical thing to try might be something like 205, because 105 didn't work. So what if we increase both of these two things here? So I tried 205, and that worked. So then I just decided immediately that I'll have 10 of those cases. And then, I just hoped the pattern would continue. I double checked a couple of them just to be super safe, but you essentially just end up with 10 copies all the way to 609. Of course, you can't go any higher than this because 9 is the top digit you can choose. So we're just going to end up with 10 cases of 6 or 6 cases with 10 inside of them. And that's 60 options in total. Good. I don't have a good method for this either. I just pretended the side length was 1, even though it tells me the area is 120. I just chose to completely ignore that. And then I broke up all of this stuff here. So this is length a half, this is length a half, because that was in the ratio 1 to 1. This was in the ratio 4 to 1, so we've got a fifth here and 4/5 there. This was in the ratio 3 to 1, so that means there's a quarter here and 3/4 there, because that's, of course, times this by 3, you get there, so 3 to 1. And then, of course, here is going to be a third and 2/3. And then I just worked out all of the areas of these triangles. So this one here, for example, is a half times a fifth, which is a 20th. And then this one here, likewise, just timesing all the fractions together. I was a bit lazy and didn't bother to write down the whole thing, but we end up with these numbers if you just multiply a half by base times height every single time. Now, of course, to work out this quadrilateral in the middle, we just need to do the total area, which I chose to be 1 times 1, which is 1, minus all of these triangles. So 1 minus all those fractions is this. I had to find the common denominator here, which I eventually did, of 120. Put those all together, you end up with this, which ends up with this. Now, this square is area 1. I was told the square is area 120, so I just need to times this area by 120, which, wouldn't you know, ends up being exactly 67 because the 120s cancel, and it ended up being okay in the end, but it wasn't that much fun. Teams get 3 points for a win, 1 for a draw, and 0 for a loss. Played 38 games and got 80 points. Won more than twice the number of games they drew, and more than 5 times the number of games they lost. I just tried stuff. I cannot stress that enough. I just tried to get some way of making 80 such that these 3 numbers add to make 38, which clearly these don't. What I did originally was actually, if you look at this, I just made them win as many games as possible and then tried to adjust from there. So this clearly doesn't work because they didn't play enough games. They only played 28 games based on this. Although I could just increase this number arbitrarily because it doesn't change the total, but it does change that rule about winning more than 5 times what they lost. So, okay, let's reduce the number of wins down a bit. I just dropped down to 22. And these do add up to make, no, sorry, these only add up to make what? 36. So we're a bit short. And I couldn't increase this anymore because then I break the win 5 times as many as they lose category. So we do have to, it seems, drop this down a little bit more, or we have to raise it back up again. Why would we raise, oh, we raise it back up again because I can't raise this at all. And I do need some extra games. So we have to raise these two instead. Of course, this maths is complete garbage, right? This just, I mean, this doesn't add up for 80. 22 times 3 is 66, plus 10 is 76. This just was a non-stop. This, I must have just written this down, hoping it would work, but it didn't, and then realized I just need to increase this. Again, there's no insight to this question other than the fact that I just tried some numbers until I found something that works, because genuinely that seems like the fastest way I was going to get done. As long as you're quick with your numbers, just trying stuff is the way to go, it seems, with Junior Challenge. So this is an interesting question. Again, there's some really interesting maths going on behind the scenes here, which you can read about in their notes, the solutions. But I mean, all we have to do really is just try the thing. So like, just start with 22 and 3 and replace 20 with the sum of these two. Replace 2 with the sum of those two, and replace 3 with the sum of those two. You get this. Now replace the 5 with the sum of these two, which is 45. Replace this with the sum of those for 27, and replace this with the sum of those for 28. I think I did it one more time. I think, yeah, I did it one more time. Now, the difference between the largest and the smallest of these is 18. The difference between the largest and smallest of these is 18. The difference between the largest and smallest of these is 18. And these two here is also 18. So pretty confident the answer is just going to be 18. When you see something like do this thing 2023 times, one of two things is going to happen. Either some immediately very obvious pattern is going to occur, like maybe it would swap 1820, 1820, and you'd have to figure out what it would be after this time, or it would just be the same thing the entire time. I mean, that's usually how it goes. Or, I mean, worst case scenario, you do have to break out something more interesting, a better way of thinking about it, but almost always it just ends up being some kind of pattern, in this case, quite trivial. If you close up this thing here into a net, what you'll see is that the 1 and the 3 are just adjacent to each other. For example, like the 1 could be here and the 3 could be here. They're just next to each other. If you close this up, they're not opposite each other. They're not opposite each other. They're because the 1 is actually opposite the 2. You can see that when you close this up very easily. Now, that's important because it means that we can just arbitrarily choose to hide the 1s in this sort of fold over here and hide the 3s here, because we can put the 1 on this dice on the back side here and the 3 on the back edge down back here, and then we can hide the 3s there, hide the 1s there, hide the 1s back here because we can just rotate this cube to have the 1 and the 3 next to each other there, and likewise hide the 3s over here as well. So all we're going to do is hide the 1s and the 3s, and the reason, of course, I've chosen to hide 1 and 3 is because that maximizes the numbers that we can actually see, because we can't hide the 1 and the 2 together because they're opposite each other. So if I put the 1 in this seam here, the 2 would be here. So hiding the 1s and 3s is the best thing I can do. So the numbers I'd actually see here would be 4, 5, 6, and 2, because I've hidden the 1 and 3, which adds to make 11, 15, 17. And then I can see that on all 4 dice, so it's just 17 times 4, and we'll end up with our answer. 25, then, he has a large number of coins. He removed some, and the mean value was 13. As soon as you see information like that, just do the mean value times the number of things, and that gives you the total value of the things. Now, I don't know how many he removed, so I'm just going to say the total is 13n, where he removed 13 coins. Now, if I remove one p piece from this, the mean value becomes 14p. So the total is 14 times n minus 1, because I've removed one of them. So therefore, 13n minus this 1p is equal to 14 brackets n minus 1. The the total originally minus the 1p that we got rid of equals the new total where there are only n minus 1 coins with a mean of 14 instead. Expand this out and then take away 13n and add 14 to both sides, and we get n is 13. So he removed 13 coins, and the total amount that he removed was 169 pence. Now, he removed 1 pence from that, we know, to get down to 168 pence, with 12 coins left over. So there were 13 coins making this, he removed 1 pence, that makes 12 coins, making 168 pence. Now, we know in this 168 pence, because it's only ones, fives, tens, and 20s, we know there must be 3 more 1 pence coins in there. So that means 9 coins are making 165. And we also know that there must be an absolute minimum 1 5-pence coin in here, because otherwise we'd never end up with this 5. So let's remove that too, and it leaves 8 coins to make 160. But the only way to make 8 coins make 160 is having all 8 of those coins be 20p's. And therefore there are 0 10p coins at all, and that's the entire challenge. Thanks for watching, and I'll see you next time.